Hello, my name is Paul Geyer, and I'm here to chat with you today about exterior electrical power distribution systems. This is what I will be talking about, kind of the chapters in the book, if you will. And by way of introduction, this is just a little bit about me and what I've been doing for the last few decades. This discussion provides guidance for design criteria and standards for electrical power and distribution systems. The information provided here must be utilized by electrical engineers in the development of plans, specifications, and calculations and must serve as the minimum electrical design requirements. It's applicable to the traditional electrical services customary for design bid build construction contracts and for design build construction contracts. Project conditions may dictate the need for a design that exceeds these minimum requirements. On-site generation is not addressed in this discussion. The design criteria and standards contained within are the minimum requirements acceptable for installations for efficiency, economy, durability, maintainability, and reliability of electrical power supply and distribution systems. The criteria and standards herein are not intended to be retroactively mandatory. Comply with the requirements of NFPA 70 and IEEE C2. Many facilities have an existing overhead and underground distribution system that has been in service for many years. As part of any new design project, review the existing design with appropriate personnel to determine which existing features should not be duplicated in future designs. Address design preferences with responsible engineering and operations personnel as part of the system design analysis. NEMA C 84.1 establishes typical voltages and voltage ranges for 60 cycle 60 Hertz systems. Facilities located outside the United States must also comply with the applicable host nation standards. Design primary distribution system equipment installations with future periodic maintenance as a principal consideration. Equipment must be capable of removal from service while minimizing the outage time of affected facilities and missions. Looped and alternate feed designs are essential to allow periodic maintenance. Provide maintenance criteria with the design analysis as part of the basis for the design. All main and electric supply stations and substations shall conform to the requirements of IEEE C2 Part 1 rules for the installation and maintenance of electric supply stations and equipment as follows. Electric supply stations shall be defined as stations that transform the energy level, the voltage, for further bulk distribution at medium voltage levels. The low voltage equipment in a main or electric supply station, equipment that is being served with from a utilization electric supply station, shall conform to the requirements of NFPA 70. The main electric supply station is the installation utility interface point where further transmission, distribution, and utilization of electrical power, the monitoring and control of such power or equipment, and the protection of electrical equipment or systems usually becomes the sole responsibility of the owner or their contracted representatives. Coordinate the design of new stations or modifications to existing stations with the supplying utility and with any other suppliers or users of power supplied. Utilization electric supply stations are defined as equipment such as pole or pad mounted transformers or secondary unit substations that transforms the energy level, the voltage, to a utilization voltage for consumer use. Some examples of utilization electric supply stations are service transformers serving low voltage equipment in a main electric supply station, a lighting transformer serving equipment for a roadway lighting system, a pole or pad mounted transformer serving a building, or a secondary unit substation serving other electrical systems. Overhead facilities shall conform to the requirements of IEEE C2 Part 2, Safety Rules for the Installation and Maintenance of Overhead Electric Supply and Communication Lines. Underground facilities shall conform to the requirements of IEEE C2 Part 3, Safety Rules for the Installation and Maintenance of Underground Electric Supply and Communication Lines. Design new primary distribution systems as 4-wire multi-grounded systems that are Y-connected at the source transformer. Provide a system grounded neutral conductor throughout the system. The neutral shall be bare copper for overhead systems. When a project is limited to connecting to an existing 3-wire system and the primary electrical characteristics are established and defined, continuation of the existing system shall be permitted with the following requirements. For extensions from underground structures, provide a 4-wire extension. Bond the grounded neutral conductor at each end of the extension to the applicable grounding electrode systems. For extensions from overhead pole lines, provide a 4-wire extension. Bond the grounded neutral conductor at each end of the extension to the applicable grounding electrode systems. Note: design of the extensions as 4-wire systems does not change any circuit classifications. It provides an extended grounding electrode system to facilitate any future circuit conversions to 4-wire systems. Provide equipment foundation pads and ensure a minimum of 10 feet clear workspace in front of pad-mounted equipment for hot stick work. Orient equipment so that adjacent equipment will not interfere with the clear workspace. Provide bollards in areas where equipment is subject to vehicular damage. Provide primary unit substations to distribute underground medium voltage circuits. Primary unit substations shall comply with the following industry standards as applicable for the specified configuration. IEEE C57-1228 pad-mounted equipment enclosure integrity, IEEE C57-12.00 general requirements for liquid immersed distribution power and regulating transformers, IEEE C57-1280 terminology for power and distribution transformers, IEEE C57-1290 test code for liquid immersed distribution power and regulating transformers, IEEE C57.96 loading dry type distribution and power transformers, IEEE C57.98 guide for transformer impulse tests, and IEEE C37.74 standard requirements for subsurface vault and pad mounted load interrupter switchgear and fused load interrupter switchgear for alternating current systems up to 38 kV. Secondary unit substations provide secondary unit substations when secondary currents exceed 3,000 amps. Secondary unit substations shall comply with the following industry standards as applicable for the specified configuration. IEEE C57-1228 pad-mounted equipment enclosure integrity, IEEE 57-1250 ventilated dry type distribution transformers 1 to 500 kVA single phase and 15 to 500 kVA 3-phase with high voltage 601 to 34 500 volts, low voltage 120 600 volts. IEEE 57-1251 ventilated dry type power transformers 501 kVA and larger, 3-phase with high voltage 601 to 34 500 volts, low voltage 208Y 120 to 4160 volts. IEEE C57-1200 general requirements for liquid immersed distribution power and regulating transformers, and IEEE C57-12.01 general requirements for dry type distribution and power transformers, including those with solid cast and or resin encapsulated windings. IEEE C57-1280 terminology for power and distribution transformers, IEEE C571290 test code for liquid immersed distribution, power and regulating transformers, IEEE C571291 test code for dry type distribution and power transformers, IEEE C57.96 loading dry type distribution and power transformers, IEEE C57.98 guide for transformer impulse tests, and IEEE C57.124 detection of partial discharge and the measurement of apparent charge in dry type transformers. With regard to pad-mounted distribution transformers, reference criteria: pad-mounted transformers shall comply with the following industry standards: IEEE C571228 pad-mounted equipment enclosure integrity, IEEE C571200 general requirements for liquid immersed distribution, power and regulating transformers, IEEE C571234 pad-mounted compartment type self-cooled three-phase distribution transformers, 2500 kVA and smaller, high voltage 34500, grounded Y 19200 volts and below, low voltage 480 volts and below. IEEE C571280 terminology for power and distribution transformers, IEEE C571290 test code for liquid immersed distribution, power and regulating transformers, IEEE C57.98 guide for transformer impulse tests, and IEEE C571222 transformers, pad-mounted compartmental type self-cooled three-phase distribution transformers with high voltage bushings 2500 kVA and smaller, high voltage 34500 grounded Y 19920 volts and below, low voltage 480 volts and below. Use dead front construction for pad-mounted transformers unless not available within system parameters. Use pad-mounted transformers separately protected with vacuum fault interrupter equipped switches for 34.5 kV systems. Do not use pad-mounted transformers with secondary currents exceeding 3000 amps because of the size and quantity of secondary conductors. Transformers rated above 1000 kVA serving 208Y 120 volt loads and above 2500 kVA serving 480Y 277 volt loads must be in a secondary unit substation configuration. Minimize double transformations to reduce energy consumption and to minimize items of equipment. Provide 2 oil-filled pad-mounted transformers in lieu of one 480Y 277 volt service if the required 208Y and 120 volt load using dry type transformers exceeds 40% of the 480 volt service transformer capability. Connect equipment at the highest available voltage to minimize the capital cost and energy loss of transformation equipment. Three-phase pad-mounted transformers must be loop feed capable with 6 bushings. Provide 2-position oil-immersed load break switches that are appropriate for the application. If the transformer might be used as part of a loop feed design, provide 3 switches to permit closed transition loop feed and sectionalizing. If the transformer will be installed at the end of a radial supply with no intention of future loop feed capability, provide a single on-off switch. Provide a spare conduit in the high voltage section extending 5 feet out from the transformer pad. Transformer connections shall be delta Y for three-phase systems. Provide bushing-mounted elbow-type arresters at the ends of all radials and in normally open locations in loops. Provide arresters for all voltage levels above 5 kV. For medium voltage switchgear, metal-clad switchgear, metal-clad switchgear can include either SF6 or vacuum-style breakers and must consist of a single section or multiple section lineup of NEMA 1 or NEMA 3R enclosures. Either walk-in or non-walk-in construction can be provided. Medium voltage metal-clad switchgear can be provided as unit substation construction or as standalone switchgear. The sections must contain the breakers and the necessary accessory components. The equipment must be factory assembled except for necessary shipping splits and be operationally checked before shipment. Consider remote racking device designs, robots, to rack breakers in and out. Metal-clad switchgear shall comply with the following industry standards: IEEE C37.06 AC high voltage circuit breakers rated on a symmetrical current basis, preferred ratings and related required capabilities. IEEE C37.121 switchgear unit substations requirements. IEEE C37.04 rating structure for AC high voltage circuit breakers rated on a symmetrical circuit basis. IEEE C37.20.2 metal-clad switchgear, and IEEE C3790 relays and relay systems associated with electric power apparatus. Provide batteries for DC opening and closing of circuit breakers. Do not use AC or capacitor control methods. Metal-clad switchgear shall comply with the following industry standards: IEEE 37.06 AC high voltage circuit breakers rated on a symmetrical current basis, preferred ratings and related required capabilities. IEEE C37.121 switchgear unit substations requirements. IEEE C37.04 rating structure for AC high voltage circuit breakers rated on a symmetrical current basis. IEEE C37.20.2 metal-clad switchgear, and IEEE C37.90 relays and relay systems associated with electric power apparatus. Provide batteries for DC opening and closing of circuit breakers. Do not use AC or capacitor control methods. With regard to metal enclosed switchgear, do not use metal enclosed switchgear. Instead, either a vacuum fault interrupter in a unit substation configuration or an upstream pad-mounted switchgear. For some installations, as directed by the owner, utilize multi-way pad-mounted switchgear when switching, isolation, or electrical protection is required. Specify SF6 gas or high fire point liquid, non-temperature dependent insulation technology, and vacuum bottle interruption technology. Specify dead front construction with stainless steel tanks and operator full-size viewing windows for each switching way. Specify 3-position on-off ground switchways for all new construction. For switch replacements, when existing switching arrangement is on-off tie, a similar arrangement without ground position is permissible. Specify switch design which incorporates operating handles on the opposite side of the tank from the cable entrance bushings, terminations, and cables. Specify 600 amp dead break connectors with 200 amp interface bushings for each switch. Air insulated, fused or non-fused technology is not permitted. Pad-mounted switchgear shall comply with the following industry standards: IEEE C57-1228 pad-mounted equipment enclosure integrity, IEEE C37.60 requirements for overhead pad-mounted dry vault and submersible automatic circuit reclosers and fault interrupters for alternating current systems up to 38 kV. IEEE C37.74 standard requirements for subsurface vault and pad-mounted load interrupter switchgear and fused load interrupter switchgear for alternating current systems up to 38 kV. For other installations as directed by the owner, air insulated and fused switches can be used in either a live front or dead front configuration. Do not use air insulated switches in corrosive and high humidity areas unless the installation experience for the installed location confirms that switch corrosion and tracking is not a problem. Apply pad-mounted sectionalizing termination cabinets only when switching, isolation, or electrical protection for the downstream circuit is not required or anticipated. Sectionalizing termination cabinets can be used instead of inline splices in manholes or for minor loads that do not warrant the expense of pad-mounted switchgear. Sectionalizing cabinets are available up to 35 kV. Provide low-profile sectionalizing termination cabinets when the conductor size is 4/0 AWG or smaller. Do not use capacitors unless they are needed for power factor correction or to minimize line losses. Verify the need by a system analysis. The analysis must consider the potential adverse effects of transients caused by capacitor switching. Refer to TSEWG TP2 capacitors for power factor correction for additional information if power correction is considered. Underground distribution has more capacitance than equivalent overhead distribution. When converting from overhead distribution to underground distribution, provide pad-mounted capacitors on a distribution system only if supported by the design analysis. Do not automatically replace existing pole-mounted capacitors with equivalent pad-mounted capacitors. For safety purposes, include an oil switch disconnect with pole-mounted capacitors. Design overhead lines to IEEE C to grade B construction complying with the following. Limit the initial loaded conductor tension to a maximum of 50% of the conductor rated breaking strength. Lesser tensions are usually applicable and generally more preferred. Utility distribution line design is generally in the range of 25 to 35% of the rated breaking strength. Provide clearance requirements using final sag values in conformance with IEEE C2 Part 2. Limit the maximum design tensions for any conductors to 4750 pounds. All clearance values shall be based on the following maximum conductor temperatures. Copper phase conductors 167 degrees Fahrenheit. Aluminum and aluminum alloy phase conductors 194 degrees Fahrenheit. Neutral conductors for multi-phase circuits 120 degrees Fahrenheit. The maximum conductor temperature for single-phase neutral conductors shall be identical to the phase conductors. Match the existing construction methods. Match those construction methods used by the local utility when directed. Where new overhead distribution is required, route the overhead distribution along roadways and other major topographical features. The poles must be accessible for future maintenance or work. Coordinate pole locations with land use planning to ensure that new poles do not interfere with future facility plans. In situations where an applicable pole detail has not been developed, provide new detail drawings as required. Designer-developed details shall contain a level of detail equivalent to standard pole details and include material requirements. Use solid wood poles for electric distribution lines. Concrete and steel poles can be used for roadway or area lighting circuits carried underground or separately from distribution lines. Concrete or steel poles may be justified for medium voltage distribution circuits where wood poles do not provide adequate strength or where climatic conditions cause wood poles to deteriorate rapidly. Do not use laminated wood poles for electric distribution lines. Due to the increasing technology improvements with aluminum conductors and connectors and the economic disadvantage of providing copper conductors, provide aluminum conductor steel reinforced or aluminum alloys for new overhead lines and extensions of existing lines. Except for grounding systems, the use of copper conductors is prohibited without specific approval and documentation by the applicable local engineering authority. Do not use ACSR conductors in corrosive and high humidity areas. For corrosive and high humidity areas, provide ACSS conductors. Provide pad-mounted transformers rather than pole-mounted transformers for new three-phase installations larger than 75 kVA. Use only single-phase transformers for pole-mounted installations. For single-phase installations and when banking single-phase transformers for three-phase applications, apply phase-to-neutral primary connections unless installed on three-wire distribution systems. Limit pole-mounted transformer sizes except for projects involving system conversions to a different operating voltage as follows. Three-phase installations limited to 3 25 kVA transformers or smaller. Single-phase installations limited to 1 75 kVA transformer or smaller. Do not use pole platform mounting, two-pole structure, or H-frame. Do not use self-protected transformers. Self-protected transformers have internal primary fuses that must be replaced by experienced personnel. Aerially mounted installations might supply several buildings. When that's the case, install the transformers at the pole location closest to the building with the greatest load. Secondary wiring should drop directly to the building served if the span does not exceed 125 feet. Otherwise, intermediate poles are required. Pole-top switches are installed at important system locations to allow either isolation of the downstream circuit or cross-connection to a different circuit. Where ground-operated gang-type three-phase air brake switches are used with non-insulated operator handles, provide a metal plate or grate at ground level for the operator to stand on when operating the switch. Connect the metal plate or grate to the pole ground conductor as well as through a braided conductor connection to the switch handle mechanism. Include a provision for locking ground accessible switch handles in the open and closed position. Single pole knife blade switches and copper barrels inside distribution cutouts are only acceptable for use in locations where frequent switching is not expected. Provide surge arresters on the line side of pole-mounted transformers overhead to underground terminal poles, all normally open switchways of pad-mounted sectionalizing switches connected to and served from overhead lines, and underground primary metering installations connected to and served from overhead lines. Provide surge arresters on the line and load sides of gang-operated air brake switches on overhead lines, primary metering applications on overhead lines, recloser sectionalizer applications on overhead lines. Provide IEEE C37.41 rated backup current limiting fuses in series with Type K expulsion fuses on systems that are greater than 15 kV, 15 kV and lower that have available fault currents equal to or greater than 7,000 asymmetrical amperes. Note, existing systems should continue to use the expulsion fuse link type that represents the standard for that system. Do not provide automatic circuit reclosing or underground distribution circuits. Keep ground wires straight and short. Minimize bends in all ground connections. Provide underground distribution as follows: in areas where the primary distribution is already underground, in locations where overhead distribution is operationally hazardous, such as within airfield clearance zones, as required to supply pad-mounted equipment and transformers, near electronics or munitions facilities that have clearance requirements for overhead power lines, near piers and loading areas where overhead cranes operate, in congested industrial areas, and in areas where storm and hurricane can damage overhead distribution. Due to the increasing technology improvements with aluminum conductors and connectors and the economic disadvantage of providing copper conductors, provide aluminum conductors for new underground lines and extensions of existing lines. This includes all new medium voltage system designs that do not require interface, splicing copper to aluminum in underground structures, with existing copper infrastructure. Grounding electrode systems shall always be copper. The use of copper conductors is authorized for extension of existing systems in which the use of aluminum results in technical limitations such as maintaining required circuit ampacity, including derating associated with number of conductors in a common duct bank or burial depth, maintaining vase infrastructure capacity, including feeder cross tie capability, conduit size, all phases are required to be installed in the same conduit, undersized or congested structures necessitating tape splices of aluminum cable to existing copper cable. Note, if adequate space exists for the use of improved technology, heat shrink or cold shrink splices, or if proper aluminum to copper compression conductors designed for the natural offset of size difference between the conductor materials is available as a standard manufactured product, provide the copper to aluminum cable extension. Do not route primary underground utilities under buildings. Systems greater than 600 volts shall also not be routed under buildings except as a direct service entrance to a single interior transformer. Tag all underground cables in all accessible locations, such as in manholes, transformers, switches, and switchgear. Install a detectable locator tape above all buried underground circuits. Marking must meet the utility standards. The definition of the terms duct bank, conduit, and duct are often confused. Within this discussion, a duct bank consists of two or more conduits or ducts routed together in a common excavation with or without concrete encasement. Minimum conduit sizes must be as follows. Primary distribution conduits along main run between underground structures, 6-inch concrete encased. With owner's permission, this conduit size can be 5-inch if the conductor size is 500 kc mil or smaller for 15 kV and below. Primary distribution conduits on laterals and secondary distribution conduits 4 inches. Secondary distribution conduits refer to the conduit routing from the distribution transformer to the service entrance panel. This requirement does not apply to street lighting circuits, housing service drops, or secondary circuits originating from an interior panel. Telecommunication conduits 4-inch. Use type EB Schedule 20 PVC conduits, minimum thickness for conduits installed in concrete encasement. Provide at least 3 inches of concrete encasement. Use Schedule 40 PVC conduit, minimum thickness, for conduits that are not installed in concrete encasement. Bury conduit at a minimum depth of 18 inches below grade. Conduits must be 24-inch minimum depth under roads and pavement and for voltages between 22 kV and 40 kV. Apply conductor ampacity derating when exceeding the NFPA 70 maximum burial depths. Provide 3-inch clearance between conduits utilizing interlocking plastic spacers. Provide spare conduits such that at least 1/3 of the duct bank contains empty conduits. Include pull wires, pull string, or pull rope in all spare ducts. Provide a transition from type EB conduit to Schedule 40 PVC conduit before emerging from underground. Use directional boring or jack and bore techniques for routing conduits under existing pavement for roadways, aircraft aprons, runways, and taxiways. Directional boring can be used for other locations where excavation can adversely affect daily operations. For permafrost locations, use duct bank installation methods that are the standard for the owner or local utility. The term direct buried wiring refers to the direct burial of conductors without any conduit or concrete encasement. Option 1. Direct buried wiring for medium voltage systems is not allowed. Direct buried wiring for low voltage systems from the distribution transformer to the facility service entrance is not allowed. Direct buried wiring for low voltage systems is acceptable in large open areas only. Sleeve all direct buried conductors under existing roads, paved areas, and railroad tracks. Use galvanized rigid steel conduit. Sleeve all direct buried conductors under new roads and use concrete encased conduits extending 5 feet beyond the edge of the pavement. Use galvanized rigid steel or minimum schedule 40 PVC conduit. Option 2. Direct buried wiring methods for low or medium voltage systems may be allowed for certain applications as follows. All applications must be submitted to the owner for approval and supported with the required documented justification during the planning process of subject design project. Any application which constitutes part of the facility core distribution infrastructure will not be authorized. All direct burial systems shall meet ANSI C2 requirements for multi-grounded systems and shall be energized at a maximum nominal system voltage of 34.5 kV. All approved direct burial medium voltage systems shall be allowed to utilize standard concentric neutral cable design instead of the typical power cable design utilizing a separate 600 insulated volt neutral conductor. Direct buried systems shall also provide a spare conduit system with associated enclosures for all streets, roads, and parking areas to provide for future maintenance capability without having to disrupt pavements. Provide minimum schedule 40 PVC extending 5 feet on each side and capped for future use. For crossing existing paved areas, the direct boring technology authorized by the owner shall apply for installation of the direct buried system. The following are examples of applications that merit consideration. Installations for special applications in remote or extremely controlled areas. Example of such applications could be ranges or range facilities, renewable energy projects such as wind farms, or bulk photovoltaic facilities provided for the purpose of supplementing system demand loading. Housing projects utilizing residential type distribution principles of single-phase pad-mounted transformer designs and single-phase distribution principles for balanced three-phase system loading. Bulk power transfer feeder from point-to-point crossing remote or controlled real estate which will revert to public utility ownership and maintenance upon completion. The following are examples of applications that merit consideration. Installations for special applications in remote or extremely controlled areas. Examples of such applications could be ranges or range facilities, renewable energy projects such as wind farms or bulk photovoltaic facilities provided for the purpose of supplementing system demand loading. Housing projects utilizing residential type distribution principles of single-phase pad-mounted transformer designs and single-phase distribution principles for balanced three-phase system loading. Bulk power transfer feeders from point-to-point crossing remote or controlled real estate which will revert to the public utility ownership and maintenance upon completion. Directional boring is a trenchless technology method to install high-density polyethylene electrical HDPE conduit used for underground electrical distribution systems. DB methods shall not be chosen as an installation means in lieu of concrete encasement or other approved jack and sleeve techniques based solely on cost. Concrete encasement and jack and sleeve techniques always provide the best means to protect conduit and conductors. Therefore, DB is authorized only for crossing under the following: roads, parking lots, airfield aprons, taxiways or runways, not airfield lighting circuits, bodies of water, environmentally sensitive areas with appropriate federal, state, and local government approval, historical preservation areas with appropriate federal, state, and local government approval. DB is applicable to medium voltage HV underground distribution systems between 1000 volts and 34.5 kilovolts nominal, and all low voltage distribution systems less than 1,000 volts. It is not applicable to airfield lighting circuits. Use of DB technologies to install electrical conduit distribution for voltages greater than 34.5 kV nominal is prohibited. Refer to appropriate standards regarding depth of DB. The depths can be less if a detailed survey is performed and documented before starting boring. For underground structures, manholes and handholds, as examples, provide separate power and communication manholes. When power and communication ducts follow the same route, use a common trench and locate power and communication manholes in close proximity to one another and staggered. Use manholes for main duct runs and wherever shielded medium voltage cable is installed. For some projects, pad-mounted sectionalizing termination cabinets can be used instead of manholes for locations that do not have multiple feeders. Handholds can only be used for airfield lighting circuits, for other non-shielded medium voltage circuits, and for low voltage and communication lines. All inline splices must be in underground structures. Do not use handholds for splicing shielded power cables. The following equipment is prohibited inside underground structures: load junctions, separable splices, bolt T connections, T splices and Y splices on systems rated for greater than 15 kV, T splices and Y splices on medium voltage systems rated for less than 15 kV may be prohibited by some owners. Power distribution equipment including transformers and switches, individually fireproof medium voltage cables in all underground structures. Specify H20 highway loading for most locations. Structures subject to aircraft loading must be indicated to the contractor. Design decks and covers subject to actual loadings. Determine the size of power manholes by the number of circuits, voltage ratings, and splicing requirements of the cables within. Manholes shall be a minimum of 6.5 feet deep. Provide cable racks in all new manholes. When reworking cables in existing manholes, provide racks for new cables. Route cable installations inside manholes along those walls, providing the longest route and the maximum spare cable lengths. For circuits rated above 15 kV, manholes shall be a minimum of 9 feet by 12 feet in interior size. Size communications manholes for equipment and splices contained, including future projections. Manholes must accommodate racking of splice closure of largest multi-pair cable while keeping cable bending radii greater than 10 times cable diameter. Provide manhole fold-out details or exploded views for all multiple circuit primary systems and all primary systems requiring splices. Indicate the entrance of all conduits and the routing of all conductors in the manholes. Provide where splices are required, where duct lines change direction, and within 100 feet of every riser pole, pad-mounted transformer, or unit substation, unless a calculation is provided to justify a greater distance with regard to the location of the underground structures. The distance must not exceed 200 feet. Separation on straight runs must not exceed 400 feet. In situations where greater separation is desired and this greater separation is not prohibited by either excessive pulling tension or site requirements, separation of up to 600 feet is permitted. Pull boxes are used for electric circuits supplying low voltage electric loads which require conductors no larger than 1/0 AWG and no more than 1 2-inch conduit entrance at each side. Wherever larger conduits are installed, use handholds or manholes. Do not use pull boxes in areas subject to vehicular traffic. Medium voltage cables shall comply with NEMA WC74 B-type MV 105 degrees centigrade rating. aluminum or copper based on the specific applications as defined, and shall contain a 600 volt insulated neutral when required. For some owners, concentric neutral conductors are also authorized. Cables shall meet the following criteria: cable jacket, PVC or polyethylene jacket suitable for wet conditions. Insulation type, provide polyethylene propylene rubber EPR for some projects. Cross-linked polyethylene is also authorized. Do not use paper insulated lead covered PILC for new installations. The insulation level for all circuits classified as multi-grounded 4-wire systems throughout the entire circuit shall be 100% minimum. Insulation level for all other classifications of circuits shall be 133%. Use copper tape shielded cables and ensure minimum bending radii of 12 times the overall cable diameter. Use copper wire shielded cables only where existing manholes are utilized and the minimum cable bending radii of tape shielded cables cannot be realized. Refer to NEMA WC74 for cable bending radii. Use single conductor cable as a general rule. 3-conductor cable may be used only when splicing to existing 3-conductor cable. Concrete for encasement of underground ducts shall be 3000 psi, minimum 28-day compressive strength. Concrete associated with electrical work for other than encasement of underground ducts must be 4000 psi, minimum 28-day compressive strength unless specified otherwise. The following requirements shall be met for electrical distribution for residential areas. Serve single dwelling units, duplexes, and quadplexes in housing areas by single phase 240/120 transformers. Serve no more than 6 dwelling units, 4 duplexes, or 2 quadruplexes per transformer. Minimum conductor size from the transformer to the service entrance equipment shall be 3/0 copper in underground conduit. Maximum length of service lateral conductors from the distribution transformer to the service entrance device or meter base shall be 220 feet. Design the distribution system such that the available fault current at the service equipment is less than 10,000 amps. Where an underground 3-phase circuit is used to feed single-phase transformers, provide a separate 3-phase pad-mounted switch or sectionalizing cabinet with a radial supply to the single-phase transformers. Distribution system grounding, medium voltage systems classified as multi-grounded, single point grounded at source transformer either solidly or with grounding resistors, and ungrounded shall comply with the requirements of IEEE C2 section 9 entitled Grounding Methods for Electric Supply and Communication Facilities. Main electric supply stations and all supply stations consisting of equipment for the purpose of transforming the voltage level for further bulk distribution shall be designed in accordance with IEEE Standard 80. The station grounding system shall require measurement prior to interconnection with other systems and prior to station energization to assure the limits of step and touch potentials as required by IEEE Standard 80 have been attained. A utilization electric supply station is defined as any station where the medium voltage system transforms the energy level, the voltage, to utilization for consumer use on any kind of facility. Examples of some utilization electric supply stations are roadway lighting transformers, a building pad-mounted transformer, or a pier or wharf secondary unit substation. The requirement for separation of grounding conductors between classes of equipment operating in excess of 750 volts and below 750 volts shall be complied with for the design of all facilities. The exception for connecting the different classes of equipment to a sufficiently heavy ground bus or system ground cable that is well connected to ground at more than one place is the engineering basis for interconnecting the different classes of equipment connected to existing systems. Ground rod composition, minimum spacing requirements, and connection shall conform to the requirements of IEEE C2 Section 9, except that minimum dimensions shall be 10 feet in length and 3/4 inch in diameter. Ground rods shall be copper-clad steel, solid copper, or stainless steel. Sectional ground rods are permitted. All connections to ground rods below ground level shall be by exothermic weld connection or with a high compression connection using a hydraulic or electric compression tool to provide the correct circumferential pressure. Accessible connections above ground level and in test wells can be accomplished by clamping. Spacing for driving additional grounds must be a minimum of 10 feet. Bond these driven electrodes together with a minimum of 4 AWG soft-drawn bare copper wire buried to a depth of at least 12 inches. Pole butt plates and wire wraps recognized by IEEE C2 Section 9 shall not be recognized as grounding electrodes. Ground rings shall conform to the requirements of NFPA 70 Section 250. If the system is not classified as multi-grounded, utilization electric supply stations, switchgear, and sectionalizing cabinets require a 4/0 bare copper ground ring with a minimum of 4 ground rods for 3-phase service. Single-phase service installations can be modified to a minimum of 1/0 copper and 2 ground rods for the ground ring. Test wells are permitted on specific applications as required. If metal bollards are installed and are within 8 feet of the pad-mounted equipment, bond each bollard to the ground ring. For design purposes, the secondary terminals of the utilization electric supply station shall be the demarcation point between IEEE C2 and NFPA 70. The transition between the grounded neutral conductor functioning as a neutral and a grounded conductor per IEEE C2 and the grounded conductor functioning as a neutral conductor only per NFPA 70 shall be at the service point. The service point for low voltage conductors from utilization electric supply stations containing no secondary overcurrent protection device shall be defined as the line side terminals for the facility service equipment. The service point for utilization electric supply stations containing an overcurrent protection device shall be at the main breaker on the secondary side of the utilization electric supply station. This is the transition point from IEEE C2 to NFPA 70 grounding, where the service main bonding jumper is located. Metal fences for electrical equipment and ordnance facilities shall be grounded in accordance with IEEE C2 Section 9. Other metal fences that are electrically continuous with metal posts extending at least 24 inches into the ground require no additional grounding unless specifically required by other criteria. Ground all metal fences at or near points crossed by overhead power lines in excess of 600 volts and also at distances of 150 feet on each side of the line crossing. Where plastic coated fabric is used, remove plastic coating where it overlaps the post to be grounded and braze or bolt conductor to the post. Supply housing units with meter sockets only. Sockets must be single-phase 4-terminal and ringless with manual bypass device and polycarbonate blank cover plate. For all other services, provide electronic programmable watt-hour meters with solid-state demand registers, including necessary KYZ initiation hardware for energy management and control systems, EMCS, and coordinated with the mechanical direct digital control system, DDC. Locate watt-hour meters directly on pad-mounted transformers or integral to unit substations. Provide exterior lighting in accordance with appropriate standards. Provide cathodic protection in accordance with appropriate standards. Consider oil spill containment for substation transformers. Containment is not authorized for pad-mounted oil-filled distribution transformers and switches. Do not use Ascarel insulated and non-flammable fluid insulated transformers because of environmental concerns as to their insulation liquid. Provide fire protection and specify installation location for oil-filled equipment in accordance with appropriate standards. Oil-filled transformers using mineral oil can only be used outdoors. Less flammable liquid transformers may be used either outdoors or indoors. These liquids should have a fire point of not less than 575 degrees Fahrenheit. HDPE conduit shall be smooth wall, approved listed for directional boring, approved listed for electrical system installations, and minimum schedule 80, meeting ASTM D2447, F2160, and NEMA TC7. Note, HDPE conduit shall always be installed below freeze lines, and in no case shall the conduit be installed less than the minimum depths noted below. Minimum size HDPE conduit shall be 5 inches for distribution voltages greater than 1000 volts and less than 34.5 kV nominal. Conduit fill shall not exceed 30%. Installed HDPE conduit shall have a minimum ground cover of 120 inches in non-pavement covered areas and 48 inches in pavement covered areas. Minimum size HDPE conduit shall be 4 inches for distribution voltages less than 1000 volts for directional boring. For directional boring, conduit fill shall not exceed 35%. Installed HDPE conduit shall have a minimum ground cover of 48 inches in pavement or non-pavement covered areas. Minimum size HDPE conduit for branch circuit wiring less than 600 volts shall be determined by calculation, addressing as a minimum branch circuit conductor size, maximum allowable pulling tension, and maximum 5% voltage drop. Conduit fill shall not exceed 40%. Installed HDPE conduit shall have a minimum cover of 24 inches in pavement or non-pavement covered areas. The use of specific conductor or insulation types for either high or low voltage installations is not mandated here. However, the combination of a chosen conductor and insulation type may not meet the requirements for the installation methods required in the following paragraphs, where length, depth, and routing of the directional bore conduit may require an alternative conductor material and or insulation type. For example, maximum pulling tensions are different for aluminum and copper conductors. If the directional bored portion of the cable run is more than 25% of the total run length, evaluate and document the conductor D-rated ampacity in accordance with NFPA 70 Article 310.60 C2. Water jetting is not permitted. Pre-installed cable in conduit is not permitted. Drilling fluids used for DB methods shall be approved by federal, state, and local codes and authorized for use. The conduit shall be installed immediately after the conduit hole is completed. There is no restriction on DB distances provided the allowable pulling tension of the conduit and installed conductors are not exceeded. Conductor splices are not within the conduit, and maximum ampacity of conductors due to depth derating is not exceeded. A registered professional engineer shall calculate the pulling tension requirements for each directional bore, taking into consideration the HDPE conduit size and type, bend radius, elevation changes, vertical and horizontal path deviations, installed electric conductor size and type, and any conductor ampacity derating due to depth of HDPE conduit. The electrical contractor shall provide certification of compliance with the PE's design requirements. The professional engineering design process must include consideration of tensile forces and bend radii created during the installation so that allowable limits are not exceeded. Allowable tensile forces must be determined by a PE. The PE certifying the installation shall account for the conduit's allowable bend radius to prevent ovalization and kinking from installation. Ovalization of the conduit shall not exceed 5%. HDPE conduits shall terminate into concrete pad-mounted electrical equipment from either a pavement or non-pavement transitional area as indicated in figures 4.1 through 4.5. HDPE or rigid conduit shall be routed and terminated within the concrete pad such that no conductor exiting the conduit shall be bent past the vertical plane formed with the equipment pad when routed to conductor terminations and with approved insulated bushings. Refer to figure 4.1. Figure 1, figure 4.1 indicates HDPE or rigid conduit electrical equipment transition. Figure 2 indicates pavement covered area to electrical equipment transition for rigid conduit. Figure 4.3 indicates pavement covered area to electrical equipment transition for HDPE conduit 20 to 45 degrees. Figure 4.4 indicates non-pavement covered area to electrical equipment transition for rigid conduit 45 to 90 degrees. Figure 4.5 indicates non-pavement covered area to electrical equipment transition for HDPE conduit 20 to 45 degrees. Multiple HDPE conduits are permitted to be pulled through each bore. Designs requiring multiple conduits to accommodate parallel conductor installations must comply with NFPA 70 grounding and wiring methods requirements. As an example, one set of paralleled conductor requirements is illustrated in the following excerpt from NFPA 70 Article 310.4, which states the paralleled conductors in each phase, polarity, neutral, or grounded circuit conductor shall comply with all of the following: be the same length, have the same conductor material, be the same size and circular mill area, have the same insulation type, and be terminated in the same manner. Thus, using DB methods to comply with 1 from the NFPA 70 excerpt, as well as other requirements, may not be possible, especially for long boring distances. NFPA 70 has other requirements for paralleled conductor installations that must also be considered when designing for these types of installations. Note, any deviations from NFPA 70 requirements must be approved by the engineer. If the directional board portion of the cable run is more than 25% of the total run length, evaluate and document the conductor derated ampacity in accordance with NFPA 70 Article 310.60 C2. Butt and electrofusion joining means are the only joining methods approved for HDPE conduit installations and shall be accomplished by persons certified in the process in accordance with the manufacturer's procedures. Transition from HDPE to PVC shall be made using only electrofusion coupling means with approved and listed materials. Coupling means shall be accomplished by persons certified on the equipment and process. Coupling between HDPE and concrete encased duct banks from pavement or non-pavement transitional areas shall be accomplished as indicated in figures 4.6 and 4.7. Transition from HDPE to concrete manholes from pavement or non-pavement transitional areas shall be accomplished as indicated in figure 4.8 and 4.9. Figure 4.6 indicates the HDPE to PVC pavement covered area concrete duct bank transition. Figure 4.7 indicates the HDPE to PVC non-pavement covered area concrete duct bank transition. Figure 4.8 illustrates the HDPE to manhole pavement covered area transition. Figure 4.9 indicates the HDPE to manhole pavement covered area transition. Consider the following general criteria as part of any exterior electrical system design. Looped versus radial primary distribution. The alternate supply capability of a looped system for primary distribution system feeders can enable the system to continue operation even with a failed conductor. Evaluate design changes to the existing system to ensure that the potential impact of conductor failure is minimized. With regard to cross-tie alternate supply capability, the ability to remove a feeder supply from service while ensuring continuity of power is essential for a reliable and maintainable design. Feeder cross-tie capability should be provided near the beginning of the feeder to reduce voltage drop and at key points downstream to provide alternate supply capability for a portion of the feeder. Address cross-tie capability and how it is improved in the design analysis. With regard to essential facilities, these facilities require additional consideration for the exterior electrical system design. Even if the facility is equipped with standby generation, minimize single points of failure in the exterior electrical system design. Provide redundant power supplies to the facility fed from different feeders if multiple feeders are available. With regard to communications, determine communication requirements for the system, including SCADA, security, access, metering, and breaker control. Include security requirements as an input to the electrical system design. Include electrical safety as a design consideration. Equipment selection, redundancy, installation approach, and how the equipment can be removed from service can all affect equipment and personnel safety. NFPA 70B, NETA MTS, and the manufacturer's documents provide periodic maintenance criteria applicable to exterior electrical equipment. Consider maintenance requirements in the specifications of equipment and in the installation design of the equipment. As an example, a single manhole located near a substation should not contain the cables of all base feeders. In this example, the design should install multiple manholes with fewer distribution feeders located inside each manhole. Coordinate metering, system design, protection, electrical coordination, load requirements, and short circuit limitations with the local utility. If the supply station substation is owned by the utility, obtain sufficient design information for the utility-owned equipment to help establish design requirements for downstream equipment. Coordinate revenue metering requirements with the local utility. Provide an owner-owned revenue meter for the supply station substation even when the local utility meters the incoming supply. Clearly define the point of demarcation between the utility-owned system and the owner-owned system. Define ownership for the incoming utility supply lines if there are any shared equipment, such as overhead distribution with utility and owner-owned lines sharing the same power poles. Design a main electric supply station substation for reliability of service and maintenance. The design analysis for the supply station substation shall address the following. Formal design. Substations require a formal design. Address the structure and foundation design, lighting protection, manholes and vaults, grounding, lighting, protective relay, and other electrical items listed. Coordinate with the utility to provide separate utility feeders if available. The transformers should be sized so that either transformer and incoming supply line can carry the entire substation peak demand, including load increase projections for the next 10 years. Either transformer load tap changing LTC transformers or separate voltage regulators are acceptable. Separate voltage regulators wherever installed must be provided with bypass and disconnect switches. With regard to circuit breaker or circuit switchers on each substation transformer primary side for local isolation of the incoming supply. For substations with overhead bus structure, include a local load break or non-load break switch as an additional isolation device. With regard to circuit breakers on each substation transformer's secondary side, this is typically the main breaker to the substation switchgear. For substations with overhead bus structure, include a load break or non-load break switch as an additional isolation device. Provide spare breakers and evaluate the need for additional distribution system feeders. Electronic protective relays to allow circuit protection, monitoring, and event recording. SCADA controls. If a remote SCADA control is included, provide dedicated fiber optic lines between the facility and the desired control location. Obtain approval for communication systems that enable remote access. Preferred connection methods include cables in conduit or cable trays. Busway transitions are discouraged, but if they are used, it must be labeled for the application by underwriters' laboratories or equivalent. Designed for outdoor service, including a stainless steel housing and hardware for corrosion controls. Rated and braced for the maximum expected continuous current and short circuit current. Designed to control condensation and its effects, and designed to allow access for periodic inspection following the NETA MTS guidance. And that brings us to the conclusion of this brief discussion of exterior electrical power distribution systems. I hope this has been of some value to you and will allow you to address projects of this type as they come across your desk in the future. Again, thank you very much for letting me chat with you, and have a nice rest of the day.